Alright, this is the setup for the first of two ways to measure the performance characteristics of a solar cell. And so in this method, all you need is a light meter, a multimeter, two leads, some light source, and the solar cell that you want to evaluate. First thing you do is need to measure the light intensity or the power. So you're going to use the solar power meter here. You're going to press the button to turn it on. You're going to see that it is in default units of watt per meter squared. That's what we want, although we're going to convert that to watt per square centimeter, which you can do. And then we are going to shift over our decimal place by clicking this R button. And notice now we get 4 digits. And we're going to position our meter flat on the surface and then measure the light intensity. So you can see that I'm starting at 0. To power on the lamp, I'm just going to power this on, or if there's another mechanism, you'll do that. Turn that on, and then we can read off from there what the power is to record that. We'll need that for later. All right, here's the setup to measure the photovoltage. So on our solar cell, we need to connect a different lead to each pole of our solar cell. It doesn't really matter if we have these flipped around, they're just gonna invert the sign of the voltage we measure. So it's not super important, but you can see how I have it set up here. This is gonna give us a positive photovoltage. So I have one lead going into the common port, and I have one lead going into the voltage port for V. And then on my multimeter, I'm gonna switch that to DC voltage. So on this meter, DC means the straight line over the V. And so right now, this is what I'm reading. This is the photovoltage of the cell, and that's because the cell itself is not completely covered in light. There's light in this room. So you can see if I cover my cell with a box, I block out all the ambient light, I get to a photovoltage of 0. And if I remove the blockade from the path of the light, you can see that my photovoltage is up to almost half a volt, 0.463 volts. And so the difference there is my photovoltage from 0 to 0.463. And so that's our VOC, or our open circuit voltage of this cell. Next parameter we need to measure is the short circuit current. And photovoltage does not scale with surface area, so it doesn't matter how much of a solar cell you present, the voltage is always going to be the same. But here you can see that I have taped off a section of the cell so that only a small area is being exposed to light. And so you're going to want to measure the actual area exposed to light. That's the surface area of the cell. And the setup is going to be the same. You're just going to keep the same wires or leads running to the multimeter. But once you get to the multimeter, we're going to switch these leads down here. So I'm still going to use my common port, but now I'm going to switch over to A for amps instead of V for volts, since I'm measuring current. This puts the multimeter in series with the circuit rather than in parallel. That's the reason why we have to physically change that. But the cell is going to be connected in exactly the same way. And then for your meter, you want to set this to DC current. So that's the flat line over A. And we can see right now, with no light on, we're getting 0 amps of current. And if I flip my light on, now I'm sitting at roughly 0.025 amps, or 25 milliamps of current. So that is our short circuit current. Okay, so once you have the open circuit voltage and the short circuit current, how do we convert that to the efficiency of the solar cell? So what you've essentially done is take 2 points in a series of possible experimental measurements along the entire IV curve for the solar cell. That's why this is considered the shortcut. And so you have to make some approximations. The major approximation you're making is, what is the shape of the curve between the short circuit current, that's the current at 0 volts, and the open circuit voltage, which is the voltage at 0 current. And so you could imagine a pure resistor, which is not what we have a diode. Pure resistor would look like this, straight line, that's Ohm's law. And a pure ideal diode would look something like this, perfectly square, where this point in space, that's the maximum power output that we could get. And so if we knew the shape of this here, of our actual IV curve, if we could measure that, then we wouldn't need an approximation. But we didn't measure that. We just measured the 2 extreme points on the end. So we have to approximate, well, what's the shape in between here, between a resistor and a pure diode? And so the typical approximation here that's pretty generous and fair is to say your fill factor is 50%. So we'll assume a fill factor is 50%. By the way, the shape of this, the squareness of ideality, that is a fill factor. So this is 100% out here, meaning you're getting maximum power conversion, and this is less than 100% as you bend inward and become less square. So we'll assume 50%. So then the efficiency is really just the power in, the power out, what you're getting out from your solar cell divided by the input power in the form of light. So the denominator here is the light input that you measured at the beginning with the solar power meter. And so you remember from intro physics that voltage times current, volts times amps, that gives you watts. So that is power. Those two terms multiply by each other. That's why this is the power out. And then we scale that by how square this is, the approximation. So we'd multiply this in our approximation by 50% or 0.5. So we take whatever our open circuit measurement is multiplied by our short circuit current in amps, multiplied by the fill factor of 0.5 divided by the power in from the light. It's important to remember though that the light power that you measured at the beginning of this was in units of watts per meter squared, and you'll need to convert this to watts per square centimeter, and then you'll need to multiply this by square centimeters of your device. That's the actual operating area of your device that's exposed to light. That'll get rid of this part of the unit, which will give us watts here divided by watts here, multiplied by the dimensionless fill factor. Multiplied by 100%, that gives you an efficiency in percentage.